Now let's look at the technologies and policies to manage energy demand. Demand-side management is the concept to manage demand and change consumer behavior in energy use to achieve better system efficiency and grid stability. It has two fields of application. First is demand response. Demand response refers to the changes of consumer behavior from their normal consumption patterns in response to price changes and incentives. Second application is energy efficiency, which means using less energy to provide the same level of energy service. Energy efficiency is different from energy conservation. By conservation, we mean switching off lights and reduce the level of energy service demand. On the other side, efficiency means that we still have the same amount of energy service, but with better technologies, we can provide the same service by using less energy. Now let's focus on demand response first. Why do we need demand response? Why do we need to change consumer behavior? This chart shows the load curve at different hours of the day, and we do see that there is a difference between peak demand and base demand. Between peak demand and base demand, we have an increase of energy demand in some hours of the day. And this chart shows the utility dispatch curve. We can see that renewable energy, hydropower, coal, and nuclear are typically used to meet the base demand. They are not expensive in terms of the marginal cost of power production, and they are also very stable power generation, meaning that with this type of technologies, it's very hard to ramp up and ramp down quickly. And if you have increased energy demand, you need to turn on the natural gas generators and occasionally oil generators. Natural gas generators and oil generators are very expensive because they have very high marginal cost, primarily fuel cost, to produce power. But they are also very flexible. They provide very quick ramping up and ramping down so that they can be used to meet the peak hour demand. There is a huge economic motivation to curve down peak demand using demand response. The supply curve is very similar to the utility dispatch curve, reflecting the quickly increasing marginal cost of power production when you have a very high level of energy demand. So if your peak demand is reflected by D1, you have to meet that demand with very expensive power at price P1. But if you are able to cut down the peak demand in a very small amount, as reflected by D2, you are able to meet that demand with a significantly less expensive price, P2. So this is the reason why we need to change consumer behavior to curve down the peak demand so that we can avoid turning up the very expensive oil generators, at the same time avoid the reserve margins for that peak demand. So the benefit for demand-side management. Specifically for demand response, we are able to curve down peak load, and by doing that, we can avoid the quick ramping up and ramping down of expensive peak generation, and also avoid the reserve margins for that generation. By doing this, we can save the consumer money and avoid greenhouse gas emissions and the emissions of air pollutants. Similarly, for energy efficiency, we can lower the overall energy consumption and avoid reserve margins and reduce primary energy consumption so that we can also save consumer money and reduce emissions. What are the technologies and policies to do demand-side management? We have smart meters and a smart grid infrastructure. We have enabling policies for smart grid. We have dynamic pricing policies. And we have a series of energy efficiency policies. Here we focus on demand response and dynamic pricing, and we will talk about energy efficiency policies later. This chart illustrates the inefficiency caused by single fixed retail rates. Most of the consumers face one fixed retail rate for power. The fixed rate is typically set at a level that is higher than the optimal rate of off-peak demand, and typically a lower level of price than the optimal price of peak demand. The single fixed rate will encourage people to consume more electricity during peak hours and discourage people to consume energy during off-peak hours. From the economic perspective, this is an inefficient way of pricing energy. Fixed rate ignore the changing electricity system conditions. We may want to set the price at a dynamic scale so that we can approximate the real-time price of the wholesale electricity market. To do that, we can have two sets of electricity rate, peak rate and off-peak rate, so that we can have a higher electricity rate during peak hours of the day and a lower rate for off-peak consumption. Some utilities may do the peak-off-peak pricing in a different way. They provide off-peak hours for most of the time and charge peak rate during peak hours for a critical time period. For example, they only charge a higher level of electricity rate for peak hours in summer. In addition to the peak-off-peak pricing, utilities can also do time of use pricing that price can be set in advance, but the price can also vary in different hours of the day. Real-time pricing can also be done by setting the price at the marginal price of power production at a specific location, but real-time pricing faces a lot of technical challenges now. Smart meters are advanced energy meters that measure the energy consumption and energy generation of end users. Smart meters is very important for end users who have distributed generation. For example, people who own solar panels on their rooftops, farmers who own wind turbines on their farms. Smart meters can run forwards and backwards. It can measure the net consumption or the net energy draw from the grid. It reads the real-time energy consumption information and also provide reading for real-time energy consumption. Smart meters allow bidirectional communication between the utility and end users. Although smart meters are very expensive in comparison with conventional meters, many of the utilities are in the process of using smart meters to replace conventional meters. One of the reasons is because smart meters enable more distributed generations from small renewable producers. Another reason is because smart meters can reduce human error in terms of reading meters, also save utility money because they can avoid hire people to read the meters. Automatic metering infrastructure, AMI, refers to the integrated system of smart meters, communication networks, and data management systems. It includes smart meters and consumer-side equipment such as in-home displays, home area networks, energy automatic controls, and smart management systems. Smart grid is the integrated system that incorporates smart meters, AMI infrastructures, distributed generation, small renewable producers, central power plants, and end users from different sectors. Policies that promote smart grid include net metering policies, interconnection standards and rules, demand response, and dynamic pricing policies. Interconnection standards and rules enable small renewable producers to be connected to the grid so that they can sell their electricity to the grid. Net metering policies allow end users to set up distributed generation from renewable resources, and they can sell electricity back to the grid if they cannot consume the electricity they produce. In addition to this, there are some challenges to the smart grid infrastructure and policies. For example, data security is a critical issue, and the privacy concern about the information related to smart meter data. For example, address and person information related to the readings of smart meters. How do you protect that information? And making sure it is secure is still a challenge. At the same time, different ways of transmitting the smart meter data back to utility, either through power line communication or radio frequency, also raises problems of public health and uncertainties and risks of those type of data transmission.